Okay, so in this video, I'm going to show you a handful of practice problems about the net force and applying Newton's second law. So the net force, let's just talk about that first. The net force is the sum of all forces acting on an object. And let's remember that the net forces act separately in the x and y direction. So the net force in the x direction along here, the x direction, and the net force along the y direction acts separately. So we need to do those separately as we go through these problems. To find the net force, the sum of all forces is just adding up all the forces that are acting on an object. So that's what net force is. We'll get some practice of that. And then Newton's second law, remember, says that when there is a net force, it's going to equal directly the mass of the object. I'm going to write it all out. Mass times the acceleration. Acceleration of the object. So net force equals ma. So we're going to use these two things to solve a bunch of problems here in this quick video. All right? So let's start out. A 75 kilogram person is in an elevator traveling at a constant velocity of positive 3 meters per second. Calculate the normal force. So, reading the question, a couple key words that stick out are constant velocity, and we're given a mass of 75 kilograms. First, you have to understand that when you have a constant velocity, the net force is equal to 0. So, constant velocity, net force equals 0. All right, so that's a really important first thing to notice. So let's draw a force diagram on this person. So here's our person in an elevator, and they're going up at positive 3 meters per second. Not an acceleration, a velocity. So we'll find out that that positive 3 isn't really going to be a part of this question that much. If we draw a force diagram, we know that the person has weight, Fg, and we know that this surface right here is applying an upward force on the person, or else they'd be flying through the floor. That is the normal force. So we know that the net force is equal to 0. We also know that the net force is going to be the normal force minus the force of gravity. I put the minus sign there because force of gravity goes down. The normal force minus Fg is going to equal 0. We know there's no difference between those two. So that's one of the equations we can write for this example. Since we know they're equal, we can put equal signs. Now we can solve for a value here. The force of gravity is just going to be the mass times the acceleration due to gravity. Well, we know that we have a mass of 75 kilograms. And we know that the acceleration due to gravity is 10 meters per second squared. So we get 750 newtons. So our question is asking, calculate the normal force. Well, the force of gravity is 750, and we know that the normal force is equal to Fg. We get 750 for our normal force. There we go. There we go. So 750, 750. Only because it was at a constant velocity. This is a pretty easy first problem here. All right, let's go to our next one. A 75 kilogram person is in an elevator accelerating downward at a rate of 2.5 meters per second squared. Calculate the normal force. Same question, but now we have an acceleration of 2.5 meters per second, and it's downward. We need to recognize that. Still a 75 kilogram person. So let's go right ahead into making our here's our little picture of what's going on. There's an acceleration equals negative 2.5 meters per second squared. So let's draw a force diagram. Now we know that there's acceleration. So when there's acceleration, there's unbalanced forces. In other words, there's a net force. The acceleration is going downward, so we would expect that our downward force of Fg is going to be greater than our upward force, which is still the normal force applied by the elevator. But now we can't exactly say that these two are equal, right? Because there's an acceleration, so we can't say they're equal. So this is where we use what I like to call the two-equation method. We're going to make two equations for the net force. Two equations for the net force. The first equation is going to be just adding up all the forces that we have on our force diagram in that direction. So actually, to make this a little more specific, we can say these are the net forces acting in the y direction, because that's what we're focused on. Let me go ahead and zoom in on this a bit. Okay, so only acting in the y direction. So let's just look for this first equation. What are the forces acting in the y direction? Well, we have a positive Fn, and then we have a negative Fg. So those are just the forces acting in the y direction. Easy. We just added them on there, making sure to include negative signs when they're down and positive signs when they're up. Our second equation is just Newton's second law, which says the net force in the y direction should equal the mass of the object times the acceleration, and to be specific, the acceleration in the y direction. This whole example is in the y direction, so we already can kind of understand that. Now we have two equations that both equal the same thing. Whenever you have two or any more equations than two, you can have as many as you want. Whenever you have an equation that equals something and you have another equation that equals the same thing, then you can say that these two must equal each other, right? Because they both equal the same thing. So let's do a little substitution and just set these two equal to each other. Positive Fn minus Fg equals the mass of the object times the acceleration in the y. Great. We've done that without any numbers so far. Let's go back and see if we can put some numbers into this equation. We can calculate the weight of the object, and we can do that by doing 75 times 10, 750 newtons. Now in the last problem we were able to say that that equaled the normal force, but again, we're not doing that this time because there's unbalance in those forces. So let's go over to this equation here and let's put in what we know. Well, we don't know the normal force. That's what the question is asking. But now we know that Fg is 750, making sure we keep that negative sign in there. And that should equal the mass of the object, 75 kilograms. And we know the acceleration is downward at 2.5 meters per second squared. So let's put a minus sign to show that it's downward, 2.5 meters per second squared. All right, great. Now we're going to do a little bit of calculation here. I'll get my calculator up on the screen here so we can see this. All right. So first we're going to do a 75. Oh, there's a little bit of a glare there. 75 times negative 2.5. So we know this side of the equation is going to equal negative 187.5. And we'll keep this side over here. 750 newtons. Positive Fn. Now we want to get Fn by itself. So what do? We add 750 newtons to this side. This will be a newton here. And we add 750 newtons to this side. These will cancel out, giving us just Fn equals, well, negative 187.5 plus 750 will give us 562.5 newtons. Great. So we calculated our normal force, which is what the question was asking for. So if we go to our diagram here, we could say this is 562. I'm breaking my sig fig rules here, but that's okay. Newtons. And we would expect, looking at this diagram, that there would be downward acceleration because this 750 is greater than this 562. All right, so that's how we check. Is there a greater force pulling it down to cause that negative acceleration? All right, let's do another one. Okay, so now it's the same thing, but now we're traveling upward, accelerating upward, not just traveling, accelerating upward, positive 1. We're looking for the normal force, 75 kilograms. I'm going to fly through this one because this is our second time doing it now. So I'm not going to draw a picture. I'm just going to draw the force diagram. Weight down, Now the normal force is going to be greater than that weight because we have upward acceleration. Right. We're going to draw our two equations. And they're both in the y direction. This one's going to be positive Fn minus Fg, same thing as last time. And this should be MAy. Set those equal to each other. Good. Now we know Fg, still 750. So let's go ahead and plug in what we know. Positive Fn equals, or minus 750 newtons equals the mass of 75 kilograms times, now be sure we're not putting a negative sign, we're putting a positive sign actually on this 1 meter per second squared. Now we do 75 times 1, we're going to have 75 newtons minus 750 newtons equals, get that Fn in there. Okay, now we want to get Fn by itself, so we add 750 newtons, we add 750 newtons, and we're going to get that the normal force is just equal to 75 plus that 750, it's going to be 825 newtons, and it's going to be positive, which is exactly what we have here. 825 newtons. And we see that that makes perfect sense, that there should be a greater normal force than the force of gravity, because it's accelerating upward. So this is our normal force right there. Great. All right, we're going to do another example. Okay, now we're no longer in a elevator. A person is applying a 200 Newton force to a 50 kilogram box on a frictionless surface. We want to calculate the acceleration of the box. Okay, so here's our picture. No friction. No friction. A 200 Newton. So there's a force push equals 200 newtons. Here's our person across a frictionless surface, and this has a mass equal to 50 kilograms. All right. So there's our little picture. So we are going to make our two equations for this example. Or actually, before we do that, let's draw a force diagram. Always draw a force diagram. Sorry. Okay, we know we have a force push starting at the object, going outward. Force push equals 200 newtons. Now, you don't want to stop there. You want to include all the forces that are acting on this object, even if they're not going to be so important to the problem here. There still is a weight, right? There has to be a weight, Fg, and there has to be a normal force on this object. And those, in this case, are going to be equal because the box is not accelerating through the floor. But that's about all we need to say about the forces in the y direction. We want to focus on the forces in the x direction in this example. So our two equations, net force in the x, net force in the x. Well, if we sum up all the forces in the x, we just have a positive Fp, which equals positive 200 newtons, right? And we know that the second equation is just Newton's second law. All right, now we have two equations that are equal to the same thing. We can set them equal to each other. I'm just going to skip a step and just say that 200 equals this. So positive 200 newtons equals the mass times the acceleration of the x. Positive 200 newtons equals the 50 kilograms times the unknown acceleration in the x. Divide by 50, divide by 50, and we get 200 divided by 50 is going to give us 4 meters per second squared. It's going to be positive because we know that the push is in the positive direction, equals the acceleration in the x. Just like that, we found our acceleration in the x using these two equations. All right, I think this is our last example here. Now we're going to give an acceleration, same example, we're going to give an acceleration. We're also going to consider a surface with friction. Mass is still 50 kilograms. There's still the 200 newtons of force as a push. Now we're going to try to figure out the unknown force of friction. Okay, so we know the mass, we know the acceleration, we know the force of the push. We know there's friction, but we don't know what the force of friction is. So this one's a little more complicated, but we have all the tools to answer it. So let's go ahead and just draw a force diagram. So 200 newtons force push, 200 newtons. We'll say that's the positive direction, positive, negative here. There's still weight. The box has weight, but there's a normal force that cancels it out. Now there is friction on the surface, so we're going to have an unknown force of friction. We know, though, that there's still acceleration in the positive direction here. This should have a positive sign. There's still positive acceleration, so we know that this force will be much bigger than that force there because there's net force accelerating that way. So this is a pretty good force diagram to start. Oh, we can put equality marks here. They're not going to be very important to our equation because we're only really looking at the unbalanced forces in the x direction. So let's go ahead and make our two equations. We really only need them for the x direction. When we sum them all up, we know there's positive 200 newtons of push minus, because this is in the minus direction, the unknown force of friction. There we go, that's our first. Our second is just Newton's second law, m times the acceleration in the x. What do? Set them equal to each other. Positive 200 newtons minus the force of friction equals the mass times the acceleration in the x. Alright, now which pieces do we have? Well, turns out we have every piece that we need to solve. 200 newtons. We don't know the force of friction yet, so let's just leave that there. Times the mass, still 50 kilograms of mass, and it's 3 meters per second squared, positive 3. Alright, now we're just trying to solve for this variable. Well, we can solve this side. 50 times positive 3 is 150, and that'll become a newton, a kilogram times a meter divided by a second squared. And we have positive 200 here, minus the force of friction. We want to get force of friction by itself, so we're going to minus 200 newtons, minus 200 newtons, 150, this will cancel out. 150 minus 200 is negative 50 newtons. And we get minus force of friction equals negative 50. There we go. So we can see that the force of friction is going to be 50 newtons. 50 newtons. The force of friction that's resisting that force of push is going to be 50 newtons. So using our two equations, we were able to solve for that unknown force of friction.